Hey class, this is just a supplement to general chemistry as related to our American Chemical Society standardized examination. What we're going to be covering is some topics that we may or may not have covered too in-depthly or too strongly as we have covered the past year of chemistry. So, getting into it, one of the first ones is phase diagrams, essentially showing from pressure to temperature how a material will exist, whether in a solid, liquid, or gas state, or somewhere in between 2 or 3 different states. For these, what we care about is going from solid to liquid and gas, or some combination of any of those two. And an additional unit that we need to keep in the back of our heads is whether or not these processes are endothermic or exothermic. An endothermic process is any one of these phase changes that requires an absorption of heat energy into the system, into the material, to transition that phase change. And exothermic processes are those where a loss or release of heat away from the system is necessary to occur. And the standard ones we have between solid and liquid is melting and freezing. Between liquids and gases would be vaporization and condensation. And between solids and gases, there's sublimation and deposition. An example of what you might see is some phase diagram, everything's blank, and we're just looking at describing what process is happening. So looking at our pressure versus temperature plot diagram, perhaps we have process A, which is, if we remember our main plot, that's going from liquid to solid. So that would be known as freezing, and because that's associated with a loss of heat away from the system, that system has to lose heat. That would be called exothermic freezing. Now, in process B, where we are going from the solid region to the gas region of our PT diagram, that is sublimation. And because to go from solid to gas, heat energy needs to be absorbed by the system or absorbed into the system, that in order to make that transition, that would be an endothermic sublimation process. Another topic that we may not have covered too in-depthly is average atomic mass, and essentially the masses for each element on the periodic table, whether in atomic mass units or grams per mole, same exact meaning. Those that we see on the periodic table are actually weighted sums of the average isotope of that element. So for example, if we were to take the average atomic mass through a calculation, we would need the weights, either grams per mole or atomic mass units, of each common isotope or known isotope of an element, and their relative abundance. Essentially, out of any 100 of this element, what percentage is in this particular isotope, and which of them is in this particular isotope. For example, from our chart, we have some element that has 3 common isotopes, either 92, 93, and 96, with the following relative abundance of occurrence: 25, 68, and 7% roughly. And their AMU weights are 92, 93, and 96, give or take the decimals. If you're asked to solve for the average atomic mass of this particular element, simply take the mass of each isotope, multiply each mass by their relative abundance, and then sum up all of those different products, which in this case, if we were to take the relative abundance of each isotope multiplied by their atomic mass weight, that would, and then sum up all of those individual products, we would get an AMU for our average atomic mass of element X being 94.74 AMUs, or 94.74 grams per mole. Another topic that we looked into enthalpy and Gibbs free energy a lot, and those are related parameters because they're in units of energy or molar energy, energy per mole. Entropy is another thermodynamic property that follows the same types of math, but it's different in that it's a unit of energy per unit of temperature, or joule per Kelvin, or joule per Kelvin mole, if we're looking for molar entropy. Entropy is sometimes called chaos, but that is wrong. Chaos is a very different property in physics and chemistry. Entropy is actually disorder, which is proportional to the degrees of freedom or the range of possibilities the atoms, elements in a substance or in a system can actually take. And we can look at these in a physical change. For example, if we look at from solid to liquid to gas, we're seeing initially a structure that has high order or well-defined shape and volume. And as it transitions from solid to liquid, it no longer has a defined shape. So those liquid atoms, liquid molecules are able to flow around with greater degrees of freedom and motion while still maintaining the same volume. That transition from solid to liquid is an increase in entropy or results in positive entropy. And from liquid to gas, well, we no longer have a defined shape or volume. So that also gives a greater range of motion or greater degrees of freedom for the particles of that system, therefore also increasing entropy. We can also look at it in a chemical reaction of taking some solid sodium chloride, which is in a high ordered state, and letting it dissolve into water, which now has free flowing sodium ions and chloride ions in the aqueous state. Well, this type of process, which allows for an ordered material to increase into different options, or in this case, increase in ions, that is an increase in entropy as well. That would be some positive increase in entropy. But if we were to look at the chemical reaction of molecular hydrogen and molecular nitrogen reacting to form ammonia gas, let's look at it this way. We have 3 molecules of hydrogen gas and 1 molecule of nitrogen gas on one side, and they are being compressed into 2 molecules of ammonia gas. We are decreasing in our options, or the system is decreasing in options for how it can rearrange those elements. It is increasing in order, so that would result in a decrease in entropy or negative entropy, a negative change in entropy. Gas molar volume, or the molar volume of a gas. Essentially, this comes from the ideal gas law, or even the real gas law. Looking at the ideal gas law, PV equals nRT. If we wanted a volume per mole amount, or V over N, that's just R times temperature over pressure. Now, what this implies is if we have any gas and we have, say, 5 moles of helium gas and 5 moles of oxygen gas and 5 moles of argon gas, and we have all those moles of gas at the same temperature and pressure, well, then that means that as long as their mole amounts are equivalent, then they have to occupy the same volume. No matter what type of gas we're looking at, as long as the mole amounts are equivalent and we're keeping temperature and pressure constant between each gas. Some different standards that are used in chemistry are the standard temperature and pressure system, or STP, which is just simply 1 atmosphere and 0 degrees Celsius. Plugging in those values, converting everything to either Kelvin and then using the appropriate gas constant, that would give us a molar volume for any gas at standard temperature and pressure, being 22.4 liters per mole. Standard ambient temperature and pressure, or STAP, is 1 atmosphere and 25 degrees Celsius, which approximately is 24.47 liters per mole. And then normal temperature and pressure, or NTP, is just 1 atmosphere and 20 degrees Celsius, or 24.06 liters per mole. There have been some systems that have been looking at 1 bar instead of 1 atmosphere. They're very similar in amounts. 1 atmosphere might be 1.0 something bar, or it might be the other way around. But essentially, we're still commonly using systems of 1 atmosphere to certain temperatures. Now, what you might see on a ACS test is something that asks you to compare the volumes of different amounts of gases. For example, what if we had 10 grams of water vapor, 10 grams of nitrogen gas, and 10 grams of neon gas? Which would occupy the greatest volume at standard temperature and pressure? Well, since molar volume is comparing volume and moles, we need not our gram information, but at minimum our mole information. So taking our grams and converting everything to moles, what we see is that if we start out with equal gram amounts, the gas with the lowest molecular weight occupies the highest mole amount. And if we were to go further, if necessary, to find volume, what we see is as we go from moles to liters of gas, the more moles of gas we have, the more liters of volume that gas has to occupy. So in this case, if we start out with 10 grams of water, nitrogen, and neon gas, it would be that 10 grams of water that would occupy the greatest volume of space because it has the most moles in that gram sample compared to any other gas sample we're comparing. Another thing to note is logarithm rearrangements. For your ACS exam, you will be given necessary equations. For example, for thermodynamics, for electrochemistry, you'll be given your equations that you're expected to use, but you won't be given the necessary information on how to rearrange different parts of those equations. So let's look at common things like logarithms that we would have to rearrange. Now you might see the function log of x or log of some internal argument. That's really log base 10 of x. And natural log of x is really log base e of x. If you need to get what's inside that logarithm by itself, well, let's look at log x equals 2. Simply raise both sides of the equation by the base of that logarithm. Since log is just log base 10, if we take 10 raised to the log of x and set that equal 10 raised to 2, a logarithm that is the exponent of its base, that is the exponent of its base, just cancels out to become its argument, or whatever was inside those parentheses. So in this case, 10 raised to the log of x, that's just x, and whatever we did to the other side, 10 raised to the second power, just becomes 200. Or, my apologies, 100. That should be 100. There we go. Made that slight little change. 10 squared or 10 times 10 is 100. Watch out for mistakes like that. Simple things like that can lead to errors on any standardized test. Now let's say we had something inside a natural log expression that we want to get by itself. Whatever that is, it could be an equilibrium expression constants or a comparison of constants like k2 over k1. Well, natural log is just log base e. Therefore, if we raise both sides of our equation to the, if we raise each part of our equation as an exponent to the e value, then e raised to natural log of x just drops down to x. And then we have e raised to what was ever on the other side of our equation, which if it's 0, then e to 0, that's just 1. Groovy. Another thing is titration curves that we can emphasize for titrations. This particular titration curve is for starting with an acid and slowly adding base. The exact opposite shape would be seen if we had a base and we were slowly adding acid, therefore slowly decreasing in pH. Now in this case, with an acid and slowly adding base, it's easy to see where the equivalence point is. That is where we have our sharp vertical region. And something of particular value is associating the equivalence point with the equivalence volume. Something particularly interesting is the half equivalence point, and it's easy to find that point by simply taking our equivalence volume and dividing it by 2. If our equivalence volume was at 50 milliliters of base, then divide that by 2 and look at the pH associated with 25 milliliters. Well, that'd be roughly about maybe 4.5 pH. Here's why that's particularly interesting. At the equivalence point, we've added enough base to neutralize all of our starting acid or to equal the amount of our starting acid's concentration. Therefore, the half equivalence point is where we've only added half the amount of base to neutralize half of our starting acid concentration, or to convert half of our acid into its conjugate base. Therefore, if we look at our buffer equation or our Henderson-Hasselbalch equation for acids, that would be pH equals pKa plus log of our conjugate base over acid. Well, since the conjugate base and acid concentration are equal, that is log of 1 or 0. So pH equals pKa at the half equivalence point, or this buffer region of a very slow rise in slope with respect to adding more and more base. The key here is just understanding if you know where the equivalence volume is, then just cut that in half and then look up, or go up to the pH point, go up and over, and that tells you the point where pH equals pKa. Or the exact opposite, pOH equals pKb, if we were looking at a base slowly being neutralized with acid. Other trends are periodic trends. Essentially, one fascinating periodic trend is looking at our neutral atoms or neutral elements on the periodic table. Let's look at the atomic radii. Well, on average, as we go from left to right on a periodic table, as we go further right in a period, the atomic radii tend to decrease. That's because we have the same outermost energy levels. We're not adding more layers to our nuclei, but we're adding more and more positive charge to our nucleus, such as going from lithium to beryllium, or going from potassium to calcium, all the way to arsenic. As we are adding more and more protons to our nucleus, that greater positive center of charge is going to more strongly attract its electron cloud. Therefore, as we're adding more and more protons, we are bringing in those outer electrons closer and closer together, therefore causing the atomic radii to decrease as we move right on the periodic table. Now then, as we move down, atomic radii tend to increase. That's because we're now adding more and more energy levels. For example, from hydrogen to lithium, we have the 1s orbital as our outermost orbital. Now for lithium, we have the 2s orbital on the outside. Or as we go to sodium and potassium, we now expand that to 3s and 4s. Essentially, as we go down a periodic table, our layers of orbitals around our nucleus are increasing or spreading, or we're getting more and more layers. Therefore, the outermost electrons are able to occupy space further from the nucleus. So, moving from left to right, we're decreasing in atomic radii of neutral atoms because the greater positive charge is more strongly attracting its electron cloud. As we're going down, we're increasing in atomic radii because we have more orbitals now, or further orbitals from the nucleus for electrons to occupy. Ionic radii have a little bit of a nuance. If we're talking about cations or anions, no matter what we're talking about, as we're going down the periodic table, relative ions still increase in radii or ionic radii. That's because, again, we have greater energy levels further from the nucleus. for our electrons to occupy. But let's look at, say, going from left to right for cations. Well, for cations, as we go from left to right, the ionic size or the ionic radii of relative ions across the periodic table decrease. The reason being, we still have increasing positive charge, but now we have less negative electrons around our nucleus relative to the neutral form of that element. For example, potassium, its ionic radius is shorter than neutral potassium because that positive nucleus is now more strongly attracting the remaining electrons. And calcium ion has a shorter ionic nucleus than its atomic, or has a shorter ionic radii than its atomic radii, because that increased positive center is more greater attracting the remaining electrons. And as we compare elements or ions in a row on the periodic table, the radii for the ions continue to decrease because similarly we have greater and greater positive charge that is now no longer balanced by negative charge. So the greater positive charge further grabs onto and attracts the remaining electrons. So from left to right, our cations are decreasing in ionic radii. And from top down, they are increasing in ionic radii. And relative to their neutral atoms, all cations are shorter in ionic radii than their neutral atomic radii. Let's look at anions, though. Here, we're taking neutral elements and we're giving them more electrons, or expanding the amount of electrons that are orbiting those nucleus. So, where before we had a balance of positive negative charge, now we have more negative charge. This results in anions always being larger in an ionic radii than their atomic radii, because that positive center is now contending with more electrons, so it's not holding on to all those electrons as strongly as when it was neutral. Now then, as we go from left to right, the ionic radii still decreases for ions, mainly because as we're going from left to right, our positive amount of center is increasing, but the amount of unbalanced negative charge is decreasing. A nitrogen anion has 3 units of negative electrons. Oxygen has 1 more proton, but now the oxygen anion only has 2 electrons in excess. And fluorine has 1 more proton, but it has 1 less excess of negative charge relative to the oxygen anion. So increasing positive nuclei, but less and less excess of electron density allows those nuclei to better attract whatever excess they do have as it's going from left to right. And then going top down, still we see that the ionic radii is increasing from the top of the periodic table to the bottom because of greater number of energy levels further from the ionic nucleus, or from the element nucleus. So for atomic radii tends to decrease from left to right and tends to increase from top down, no matter what. And for ionic radii, for just cations or just anions, the ionic radii tends to decrease from left to right or increase from top down. It's just that compared to their neutral atomic radii, cation ionic radii is always shorter than the atomic radii, and anionic radii is always larger than their neutral atomic radii. And then lastly, just one last periodic trend. As we get closer to fluorine on the periodic table, elements tend to be more electronegative or more greedy for electrons. They tend to be the elements that like to have partial charges on them. Uh, partial charges on them. And so essentially, as we're looking at the top right of the periodic table, as we get closer to francium, or the bottom left of the periodic table, those elements tend to be more and more metallic. In any case, that concludes our little supplement to general chemistry for our upcoming ACS exam. Hope it all goes well for all of you, and looking forward to seeing how you all do. Peace.